Hello, so today we're going to talk about the idea of what a complex number is. So again, following along in the Glencoe Algebra 2 textbook, 2018 edition, we're in section 3.4. So an imaginary number is defined as the square root of -1. So if you remember from Algebra 1 or geometry or pretty much any time you've ever talked about square roots, and if your teacher was careful, they never, when they did like square roots of negative numbers, they're like, oh, that doesn't give you a real result. They didn't say it wasn't possible. They said it didn't give you a real result. Because it gives us what we call imaginary results. Now, I know what you're thinking. Imaginary numbers? Like, are you serious right now? Like, are we talking about, like, it's going to be like unicorns and other, like, dragons and stuff like that? No. Imaginary numbers, oddly enough, have a lot of real properties in mathematics, though for the most part you kind of need to get into higher mathematical classes, engineering courses, that kind of stuff to see the real-world applications of an imaginary number. So real quick though, imaginary numbers have the following properties. I squared comes out to be -1, I cubed is -I to the fourth is 1, and you'll start seeing it repeating a pattern then. I to the fifth is I to the sixth is -1, and so on and so forth. Pretty much the way you go about trying to figure out what it is, like if they give you like I to the 179th power, what does that equal to? Well, if you just simply divide 179 by 4, and you'll want to use this by hand so you can figure out a remainder, you find that you get a remainder of 3. That means this is equivalent to I cubed. Since I cubed is -I, it means it equals -I. So that's how you would handle something like that if you see I raised to a power that's not one of these nice ones right here. Just simply divide by 4 and identify your remainder, which is why you kind of have to do it by hands. So if we want to simplify each one of these, well, if we ignore the negative, the square root of 36 is 6. So this is 6i. If we ignore the negative, the square root of 27, while not perfect, will simplify down to 3 radical 3. So it'll be 3i radical 3. And we get that 3 radical 3 because we see that 27 is 9 times 3. And the square root of 9 is 3. That's where that's coming from. We're looking for the biggest square that goes into it. So -125. Well, 125 is 25 times 5. So that becomes just 5 square root of 5. So that means this will be 5i. Square root of 5. Okay, so we're just still simplifying them the same way we would any other radical. Since it's negative, we just have to include the I there. So we're talking about these equations right here. Since there's only a single quadratic term, we can solve it by isolating the variable. So if we subtract 49 from both sides, we get x squared equals -49. And when we do our square root, again, we're going to have an imaginary number because the square root of -49 is going to give us imaginary. So we worry about the square root of 49, which is 7. So it'll be plus or minus 7i. We still have the plus or minus aspect of the number. We can't forget about that. But we also have to include the idea of I in there as well. So for this one, we subtract the 80 over first. So we get 2a squared equals -80. Divide by 2, a squared is -40. Then we do our square root of both sides. So 40, when we break it down, is 4 and 10. So it's 2 square root of 10. So this would be plus or minus 2i square root of 10. And again, this is where your calculator can really help you out. If you do the, again, graph y equals 40 over x, and look at the table of values, it gives you all the factors. In addition, it'll give you numbers like when x is 3, y is like some decimal then. But if you just go through that list and you find the biggest perfect square that's a factor, you can really make your life a lot easier to go through these problems pretty quickly. Now, a complex number is one that's written in this form, a plus bi, where a and b are both real numbers. So it'll be something like 3 minus 2i. This would be a complex number, where the a value is 3 and the b value is the -2. We call the a part the real part, and the bi is the imaginary parts. So pretty much when you're working with these, your basic algebraic operations, working with addition, subtraction, multiplication, division kind of stuff, you pretty much pretend the I is a variable and just go from there. So, if we're adding these two complex numbers together, 5 minus 7i plus 2 plus 4i, well, we just add the real parts together. 5 plus 2 is 7. We add the imaginary parts. Negative 7i plus 4i is a negative 3i. And there's our answer. And that's it. It's a very straightforward process. If we have 4 minus 8i minus 3 minus 6i, we just subtract. Real parts, 4 minus 3 is 1. Negative 8 minus a negative 6 becomes negative 8 plus 6, so it's minus 2i really. So if you want to make sure you're careful with the negative part, if you make this a plus and then change both the signs there, that might make your life a little bit easier going through the problem. But again, your call with something like that. Just combine like terms correctly and you'll be fine. Multiplying two binomials, just FOIL. 5 times 7 is 35. 5 times negative 3i is negative 15i. 2i times 7 is a positive 14i. And 2i times negative 3i is negative 6i squared. So we get 35 minus I. And then I squared is negative 1, so this becomes plus 6. The I squared term will always become the opposite sign that it currently is, and the I squared will go away, leaving us just 41 minus I for our answer. So anytime I has an exponent, you need to make sure you evaluate and redo that exponent. So when it's an even power, I squared becomes negative 1. If it was I to the fourth, it would become a positive 1 then. If it's an I cubed, then remember it's negative I, and you go from there. So your term is allowed to have an I in it, that's okay, but you want to make sure any I exponent goes away. Alright, so we FOIL this one out here, so 3 and 3 is 9. 3 and 7i is 21i. Negative 7i and 3 is a negative 21i. And negative 7i and positive 7i is a negative 41i squared. I don't know why I put an equal sign there. That should just simply be minus 21i. That was weird. You'll notice in this expression, the middle I terms cancel out. And then remember, I squared becomes negative 1, so this becomes plus 41, so it just becomes 50. Now this is interesting. We had i's originally, we multiplied the expression out, and all the i's cancel, leaving us just a positive whole number, all real. So the key to remember for something like this is this idea right here is what we call the complex conjugates. And this is important to deal with dividing complex numbers. Because when we have I in the denominator of the fraction, it is not considered a proper mathematical expression. Similar to where we can't leave radicals in our denominators. So to get rid of it, we do the conjugate, because if we multiply by the conjugate in our denominator, it cancels out the entire I from the denominator, and the problem is then okay. Because we're allowed to have I in the numerator, that's fine, we just can't have it in the denominator. So for this expression right here, we'll multiply by 6 plus 2i. Again, we change nothing about the first number, we just change the sign of the second number. So up top, when we distribute negative 5i, we get negative 30i minus 10i squared. On the bottom, when we FOIL that, we get 36 plus 12i minus 12i minus 4i squared. So the top I squared becomes a positive 10, so it's 10 minus 30i. The bottom 12i's cancel, becomes 36 plus 4. So we have 10 minus 30i over 40. And from here, it's proper to then separate out as two separate parts, the a and the bi parts. So this becomes 10 over 40 minus 30 over 40 I, which, whenever we have fractions we must reduce, becomes 1/4 minus 3/4 I. And that would be the acceptable answer right there. So again, we multiply by the conjugates, the opposite sign from the denominator expression, and we just simply distribute and FOIL and work it out and simplify the problem down to two fractions, a and a bi parts. Okay, The numerator can also be a binomial expression as well. It doesn't matter. We don't care about I in our numerator. It's all about, again, multiplying by the conjugate, so 2 plus 8i on the bottom, and then 2 plus 8i up top. So now we just simply FOIL the top and bottom. So we get 12 plus 48i plus 8i minus 32i squared. Sorry, plus 32i squared. Jump the gun with the negative sign there. And then we'll get 4 plus 16i minus 16i minus 64i squared. So up top we'll have 12 plus 56i minus 32. On the bottom, the 16i's cancel, leaving just 4 plus 64. So we'll get a negative 20 plus 56i over 68. Again, we need to make sure we write them as two separate fractions. So negative 20 over 68 plus 56 over 68i. Where now we need to simplify our fractions. 20 and 68 have a 4 in common. So it'll become a negative 5 over 17. And then 56 and 68 also have a 4 in common. So then plus 14 over 17. I. Okay, and that's our complex number I. A bunch of different ways you're going to see it. You're going to mainly see it for the rest of this particular next couple of videos, solving quadratics. The quadratic formula and completing the square both involve square roots in some ways. So you'll see your imaginary number pop up in those methods there. Never comes into play with factoring, because we generally don't factor to get an imaginary number. Polynomial expressions don't have I in it. They're not considered proper polynomials at that point. Alright, but I'll see you next time with those other videos regarding how to use I.